Hello everyone. In this video we are going to talk about the second problem in statics that you requested me solve. So here we have this car on this 3D surface. Let's say there is a platform in the car mechanic shop, and that platform, not only it can go up and down, it can also tilt. And here you have applied the brake, you like the brake, and since that's not enough to keep the car in balance in 3D, you also attach the front of the car with the cable to the wall. And if you call the contact point with the wall point B, and if you call the contact point of the cable with the car point A, the direction cosines of cable AB are given to you. Also, the vector normal to the plane EN is also given. The weight of the car is given, and you had a device to measure the tension in the rope, and you found that the tension in the rope is 1200 Newton, basically, right? So now the question is, what is the magnitude of the normal force from this platform to the car, and what is the magnitude of the friction on the car? Okay, and here we treat the car as one single mass point, not really as a rigid body. The dimensions are not given, so we consider it as a mass point. Okay, so what should we do? As you know, here, so if we call the friction F and we call the normal force N, the question is, what are these two forces, their magnitudes? And to do that, we first need to draw the free body diagram of the car. So what are the forces acting on this car? Well, for a free body diagram, you have to separate the car from the rest of the environment. You have to detach it from the cable. You have to remove the contact from the surface. So if we want to do that, let me add a free body diagram without those. Okay, so with the help of paint, I separated the car. And now the forces that we have is, of course, W. And then we have the force of the cable, T. And we have N and F. Now, N is definitely along EN, but the friction here is not as clear. Okay, first of all, the friction here is not just a simple friction along X or Y or Z. The problem is really 3D, so this friction can have components along all three axes, because the way that this car would slide down the platform and wants to basically get off the platform is the direction of motion of that is not going to be along any of the axes X, Y, Z, so friction is opposite to that, okay? If I had the location of the car, right, and consider it like a mass particle, the matter of fact is it's not really a mass particle, it's a rigid body, and when we talk about friction, it's the equivalent of friction on all four tires. But if we considered it like a mass point, and if I had the location of the mass point, point X, Y, and Z, right, and if I had the equation of this plane, then I could basically use the gradient, right, because that's what you know. Gradient is the direction of steepest descent. Hopefully you watched my video on steepest descent. If I could, again, had the equation of the plane and the location, I could calculate the negative gradient of the plane on that point. That would give me the direction of slide, and then opposite to that would be the friction. But even if I do so, that gradient will have X, Y, and Z component. So friction will have all three components. And N, clearly, since along EN, and EN has all three components, so N also has all three components. So each one of these vectors, F and N, has all three IJK components. So what I will do is, instead of both of these, I consider one single force, and that one single force, I call it F. This F is the total force, the total contact force from the platform on the car. The normal component of it to the surface is the normal force N, and the tangential component of it to the surface is what? Friction. So this F is really friction plus the normal force in this case. Okay, I just consider it as one single force. And now we try to find that equivalent force of the platform. How? By equations of equilibrium. So if we call this unknown force F, we call it Fx times I plus Fy times J plus Fz times K, where all of these components are unknown. Then equilibrium would tell me that summation of the forces along X is equal to what? It is going to be Fx component. W has, because W is what? W is the weight of the car, which is 1350 times G, and it is in the negative Y direction, so it's going to be negative 1350 times 9.81 times J. That's your weight as a 3D vector. And what about T? Well, T in this case is the tension. It has a magnitude of 1200, and the cosine vector, the cosine direction cosines of the vector, it says that connects what? From A to B, which is this unit vector basically. This guy, right? This unit vector, E of T, that is given by these three theta x, cosine theta y, and cosine theta z. So if I multiply my magnitude 1200 by these three unit vectors, or these three cosines, I'm sorry, that will give you what? The vector t in terms of I, j, and k. So if I want to write t again as a vector, this is what I can do. Let me just move this a little bit so I can have room to write my t somewhere. Like this. This t is going to be 1200 times the unit vector of t, which is cosine theta x, which is negative 0.816 times I, plus cosine theta y, which is 0.408 j, and finally minus 4.408 times k. This is vector t, which is in this direction. Okay, so any vector, as you know from statics, can be written as its magnitude times what? Its unit vector. And the unit vector, if you know the direction cosines of it, all you need is to multiply those direction cosines by ijk, and that will give you the unit vector. So here, f of x is the component of x, f in the x direction. W has no x component. T has this much of x component. So it's going to be negative 1200 times 0.816, right? And then we can go to the y direction. This is equal to 0. So from here, clearly I can find my f of x. In the y direction, I will have Fy minus weight and minus or plus 1200 times that 0.408. This is equal to 0, so that should give you your f of y, And in the z direction, I will have fz and minus 1200 times that 0.408. So that should give you what? Your f of z. So if we calculate them, we get, so here I calculated them for you, and these are the numbers. So these are the components of the force applied by the platform to the car. Now, which part of it is the normal force, which part of it is the friction? So since the problem is asking about the magnitudes of the normal and the friction, as we said, the component of it, that is along En, right? So if this is En, the component of F along En is the normal force. So if I project it along En, this is going to be the normal force. And basically, the projection of that tangent to the plane is going to be the friction. So this guy is going to be friction, and sum of these two forces is going to be what? Equal to the capital force F. So if somebody says what is N, what is F? So N, if we want the magnitude of it, is simply going to be F dot En, correct? In order to do projection along a unit vector, all we need is to use dot product. If somebody says what is N as a vector, you multiply this by En itself, right? So if somebody says what is N, we multiply this magnitude by En, okay? This is what? This is N as a vector. If we are just interested in magnitude, this is the magnitude of it, right? So N magnitude is just F dot En. So all you need is to dots product the vector with these three components with En, which has these three components, correct? That's all you need, a dot product. So if you calculate it, you should be getting 12,149 Newton. So this is the magnitude of the normal force from the surface. And now, if you want F, what you can do is to basically find the force F and then find the magnitude of it. That's one way, or you can do the parallel projection. But I assume the best way to do it is, as I said, the friction force plus the normal force is equal to cap F. So from here, the friction force is going to be F minus N. F is completely given, and N is just this magnitude along En, correct? Right, so just subtract F from this number times En unit vector. That gives you F as a vector, which if you do, you will get. So here is the friction vector calculated for you. And as I mentioned earlier, you clearly can see that the friction has all three components. It's not along any specific axis. The same thing for N. If you just multiply this magnitude by those three components of En, you'll see your normal force has all three components, right? And now we can find the magnitude of this friction force, and that is going to be 4033. But I could have found this magnitude without the need to calculate the friction force, right? Because you know, if F and N are the only components of F, then this is also equal to magnitude F squared minus magnitude N squared, right? I could use the Pythagorean theorem. And magnitude N is already found. Magnitude F, I just needed to take the magnitude of this vector, right? And then that will give you magnitude F. But the reason I calculated it, I just wanted to show you that in 3D problems like this, do not assume that friction is along X or Y or Z only, right? It has all three components in general. Again, if I had the equation of the plane, which I could find it if I knew one point on the plane, because I know the normal to the plane, I just needed one point on the plane, which I don't have, and if I knew the location of the equivalent for all frictions, maybe a center of mass or something I could have used. It's not that easy really, because you need to know all the dimensions to find an equivalent for all four frictions, an equivalent point. And then using negative gradient, I could have found the direction of friction here. But you clearly see, if you get the direction of friction from here, right, all you need is to divide this vector by its magnitude. That gives you a unit vector, right? Let me show you that before we finish this video. So here, this is this number that I calculated for friction. If I say this is equal to vector F, now E of F is equal to F times magnitude of F. No. F is this, norm of F is this, so norm of F, not absolute value. This is the unit vector, right? This is EF, and then this guy here that you see, this is EN, right? This one. So this is EF, this is EN. Now, are these perpendicular to each other? We can use a dot product and see whether they are perpendicular or not, and you see they are, right? This number is almost zero. It's just, the reason it's not perfectly zero is numerical error, the round of errors. But you clearly see the direction of this friction and the direction of normal force are perpendicular to each other. So the problem makes complete sense and your calculations are correct. So hopefully this 3D equilibrium problem for a mass point was useful to you as you requested. In the next problem, we're going to do a 3D problem of equilibrium, but we include dimensions and we consider it as a rigid body, so we need to bring in the moment equations as well. Thank you. See you in my next video.